Hi everyone, I'm here to talk to you about building storage systems for new applications, new hardware, and new metrics. Storage systems have really become the bedrock of all the different services that we use today, whether it's cloud services or mobile applications, key value stores, or relational databases. All of them have storage services as a sort of like foundation, and reading and writing data is basically how all of these services operate. Now, design of storage services today face a number of new challenges. First is that there's new hardware that's coming out. So, for example, last year, persistent memory was released by Intel. On the sort of like 5 to 10 year horizon, we have DNA storage, Project Silica, and so on. And so these are all sort of like coming out. There are new applications which stress the storage systems in new ways. For example, there's machine learning, with blockchain, and new regulations such as GDPR, which all have new constraints that they place on storage systems. Finally, design of the storage systems also have to worry about new metrics such as device lifetime. So, for example, when you were designing a storage system for a hard drive, you didn't have to worry about device lifetime. But now with solid-state drives and persistent memory, there is device wear out. So you have to worry about that and design a storage system so that you don't wear out the device faster. So there's also the new challenges in this space. And this talk is going to be about my group's attempt at tackling these challenges. And there's been a lot of wonderful work in the field by a whole range of people. And I don't want to give the impression that like my group is the only one working on this. So there's lots of wonderful work, but we're going to talk about some of the things that my group did over the past few years. So we're going to talk about how we built a file system for persistent memory called SplitFS, and an approach for building concurrent crash consistent data structures for persistent memory, which we call recipe. Both of these were presented last year in SOS3. And then we have some work that's ongoing or was published this year. We're talking about how we build storage systems specifically for machine learning, for public blockchains, and how we analyzed GDPR from a systems perspective and discuss how it impacts storage systems. So that came out in VLDB this year. We'll also briefly talk about our PebblesDB key value store, which came out in SOSP 2017, which is a write optimized key value store. So it reduces the amount of data that is written to the storage device. And we show that you can actually do this and still improve performance. So PebblesDB outperforms RocksDB, for example. So the people who did this work are like my students and my postdoc, and all the sort of like credit for this work goes to them. And throughout this talk, I'll be sort of like pointing out like who did this work. All right, so this is going to be a general outline of my talk. I'm going to be talking about new storage systems, the new applications and metrics, future challenges, and then I'll sort of conclude. All right, so first we're going to talk about persistent memory. So this is a new storage technology that came out in April 2018. So it's a form of memory, right? So just like you have DRAM today, you have persistent memory. It sits on the memory bus adjacent to DRAM. It is accessed in a similar way. So for example, the processor can issue load and store instructions to DRAM. It can do the same thing to persistent memory. Now, the performance characteristics of persistent memory is a little bit interesting. So it's about 2 to 4 times more expensive in terms of latency to do a read. The writes are about the same latency, and the read bandwidth is 1/3 that of DRAM, and write bandwidth is 1/8 that of DRAM. So in terms of write bandwidth, it's a very bandwidth constrained device, right? And the performance of persistent memory generally is much, much higher than solid state drives. So compared to the best performing NVMe SSDs that we have today, persistent memory is about an order of magnitude better performance. All right, how do you build storage systems for persistent memory or like how do you build data structures, right? So there's been lots of wonderful work. So the goal of building data structures is that we want it to be concurrent. All of our servers are multi-threaded and multi-core these days, so we want to be able to use concurrency to increase performance. We want it to be crash consistent. So if we lose power or there's a kernel bug, when you come back up, we want the data structure to be in a consistent state. There's been lots of good work in this space, going back to Nemosini, which is like one of my favorite papers from Wisconsin, to level hashing and CCEH in some recent times. Similarly, another broad goal is how do you build file systems for persistent memory. And there the goal is you don't want your file system operations to be very heavy. You don't want them to take like seconds or milliseconds. Given that the device itself is very, very low latency, you want your file system operations to be very efficient. You want the file system operations to be scalable. Like as you throw more cores at file system operations, you want the throughput to scale, right? And again, there's been lots of good work in this space. And going back to BPFS in SOXP, and even further back is like NV, for example. So people have been working on persistent memory for a long time, even though it only physically came to market last year. They've been anticipating what it will look like and building systems for it. Right? So we're going to look at some of the problems that my group tackled in this space. So the first thing we looked at is like we have software overhead for file system operations. So let's take a simple operation where you want to append 4 kilobytes to a file. Very simple operation, and in most of the applications that we have today, they are all append bin. Very few applications actually write in place. So this is a very common operation, right? So the x-axis is the different systems that we're comparing against. The first point in the x-axis is the device. So it takes about 700 nanoseconds to write to this device. The y-axis is nanoseconds. Now, if you look at the ext4 DAX, which is the mainline commercially used ext4 file system, that is about 9,000 nanoseconds to do this file system operation. So there's a 12x gap, right, between time taken on the device and the time for the file system operation to complete. So this gap is called the software overhead, right? And our goal was to minimize this gap. So if you look at like other file systems available today, like Stata, Nova, and so on, they all have done many things in order to bring down the software overhead. But even then, Stata is still like 2.5x the device latency, right? So there's still quite a bit of like room left for optimization. So in summary, current persistent memory file systems have high software overhead. So the big question that we are tackling is like, how do we decrease the software overhead of file system operations? Let's play that again. Oh, sorry. Right. So how do we decrease the software overhead of file system operations? Sort of like the central idea that we have is that we want to handle data operations in user space. So this means that file appends, for example, we want to handle in user space, reads, direct overwrites, we want to handle all of them in user space. And we actually want to route the metadata operations to an existing internal file systems, just the ext4, right? And this sort of like unique split of responsibilities is why we named the file system SplitFS, right? And my students Rohan and Sekwan worked on this. So it's a POSIX-like file system for persistent memory. It was done in collaboration with Georgia Tech, with Case of Kim and Sanjay Kashyap. And the central idea again is to handle data operations from user space, route metadata operations into the cloud. Now you might ask, like, why would we want to do this, right? And the reason is that data operations are simple to handle, right? So if you want to do a read or a write, the semantics are very well defined. There's not a lot of like different corner cases, and you can handle them simply and efficiently in user space. So you don't actually go into the kernel in order to do this. However, metadata operations are complex and hard to get right. So there's been lots of work done which show that POSIX has a lot of like weird corner cases, and re-implementing them all in user space is not, it will lead to a lot of like complexity, right? So what we want to do is we want to handle data operations in user space, but use the fact that ext4 DAX, for example, has already gone to a large amount of like developer effort to get all these puzzle operations right in order to do this, right? So that's the overall architecture of SplitFS, right? Now, if you look at like other work that's been done in this space, there's really two big ends of it, right? On the left-hand side, we have everything in the kernel. So both data operations and metadata operations have to actually happen inside the kernel. And on the right-hand side, we have both happening in user space. So on the left-hand side, ext4 DAX, PMFS, Nova, these are all file systems to do everything in the kernel. And they have low performance because of it. Because every time you want to write 4 kilobytes, you have to go to the kernel. There's lots of software layers. It's very heavy and it increases latency. On the right hand side, we have Strata, which is a completely user space file system. And the problem there is that it has high complexity. They basically had to re-implement a lot of the VFS stuff, virtual file system stuff in user space. This adds to the complexity that Strata has to maintain on an ongoing basis. And ARI from Eurosys is also similar in the space, but instead of like doing everything in user space, they use the kernel just for allocations. And our work is very similar in thought to this line of work, right? Because in SplitFS, we do data operations in user space, but for the metadata operations, we are going to leverage an existing in-kernel file system. So we get high performance because most workloads are dominated by data operations, and we get low complexity because we don't have to worry about any project's common cases, right? All of them will be handled by ext4 tags for us. We just have to focus on the data. And we truly believe this is the best way to build persistent memory file systems because it is the only way in which you get the best of both worlds. Like you get high performance by handling data operations in user space, you get low complexity by not handling data operations in user space. So this is really the best of both worlds. So this is sort of like providing sort of like a visualization of the architecture of SplitFS. So we have the application on top, and then we have the user mode component of SplitFS, which we call uSplit. And then below that in the kernel, we have ksplit, which is basically ext4 tags. And then we have at the bottom, we have persistent memory itself, right? So when you do reads or writes, the kernel component is not involved. From user space, you go all the way down to persistent memory, and you can read and write files, right? Now, when you want to create files or delete files or do any metadata operations, uSplit then talks to the ksplit, the kernel mode component, and then coordinates using that to create files. In order to have strong guarantees such as atomic data operations, uSplit has a log. And again, to read and write to this log, you don't have to go through the kernel. So it's a user space log that uSplit maintains. Okay? So to summarize, SplitFS accelerates common case data operations, reads and writes, by leveraging the maturity of ext4 DAX for metadata operations. ext4 has spent decades getting metadata operations right, and so we want to leverage that. And it uses techniques such as like logging and out-of-place updates for providing strong guarantees, such as atomic synchronous operations. These are very similar to the guarantees provided by Nova and Strata. Right? So if we look at the time taken to append 4 kilobytes per file again, we see that SplitFS is actually the lowest among current file systems. And this is because the file append is handled in user space. So the overhead that we have is 80%. This means that the additional overhead that you have versus just writing a 4 kilobyte block to a persistent memory device, the overhead that we have is less than writing another 4 kilobyte block to persistent memory. So the overhead is less than writing an extra block to persistent memory. So we use a number of different techniques to get overhead down low, and we recommend you read the paper. So check it out. And in the paper, we also have other results. So we have tested with like level DB, with the Redis key value store, with the Git, tar, and so on. And we show that when providing the same guarantees, SplitFS outperforms Nova, right? It outperforms Nova for all the data dominated workloads while getting similar performance for the metadata dominated workloads. SplitFS is open source. So this is something that my lab takes very seriously. Most of the work that we have done is open source. And we go to a lot of effort to make it well documented and easy for an external person. Right, so the code is up on SplitFS, and if you want to use SplitFS in sort of like a research project or in your company, please contact us and we'd be happy to help you do that. Right, so transitioning to sort of like the other project that we did, the main question we tackled is how do we build concurrent data structures for persistent memory, right? So the goals are, we want it to be concurrent. As we throw more threads and cores at it, we want performance to increase. We want it to be crash consistent. So this means that if we lose power for any reason, we recover to a consistent state. And we want it to be cache efficient in general, like we want it to be high performance, right? Now the thing is, concurrency and crash consistency are both sort of like complex things, and if you try to do them together, they lead to bugs. So for example, when we looked at the sort of like state-of-the-art data structures like fast and fair and CCEH, we found bugs in both, like subtle bugs due to how they constructed it. So these were all built by hand. And so our sort of like, or from scratch, and our sort of like main idea was that people have already invested like decades of research and development into building concurrent DRAM data structures. Can we exploit that in some way to build concurrent persistent memory data structures, right? Specifically, can we convert existing DRAM data structures to persistent memory data structures? So that's the chief question. And in order to actually do this, we exploit an insight. So we saw that in DRAM data structures, if they're concurrent, they usually have isolation, right? And we saw that the isolation provided by DRAM data structures is very similar to the crash recovery that we want in persistent memory data structures. So this is sort of like the big insight powering our work. And based on this, we built something called recipe. So it's a principled approach to convert DRAM data structures to persistent memory data structures. And using this approach, we converted 5 popular DRAM data structures, like hash tables, B plus trees, radix trees, and so on. And in all cases, the conversion required less than 200 lines of code. And we saw that because we converted very high performance, cache efficient DRAM data structures, the resulting persistent memory data structures have excellent performance. In multi-threaded evaluation, they beat the current state of the art, right? They beat all the handcrafted data structures that are currently present by a significant amount, by like 5.2x in some cases, right? So we believe like this is a good approach to transform DRAM data structures to persistent memory data structures. To talk about sort of like the chief insight powering this, right? Isolation ensures that if a data structure has concurrent writes going on, a read returns a correct value, right? So you know, a write may be doing some other thing, but if you've started to read some value, you get a consistent snapshot of it. Like snapshot isolation, for example, that's what it promises. So regardless of concurrent writes, reads returning correct consistent value is isolation. Crash consistency, it turns out, is very similar. Irrespective of like crashes between the write and the read, crash consistency wants to ensure that the read returns a correct value. So in the case of isolation, it's concurrent writes. In the case of crash consistency, it's a crash, right? So, but despite these things, we want the read to return a correct value. And others have noticed this connection before. The memory persistency paper from Michigan, NISCA 14, has this really nice idea about crash recovery through an external observer, right? So we want to use this idea in our work, right? And the sort of a key thing is we want to reuse the isolation mechanisms in DRAM data structures for crash recovery. And you might wonder, like, how do we do that? Like, we seem sort of like far apart. And let me actually provide sort of an example. So lock-free data structures, for example, do not hold locks in the read part. So a reading thread may encounter a partially done write, right? So one thread is reading, another thread is writing, and because the reader is not holding the lock, the reader may see the partial result of the write. The readers can tolerate this inconsistency. So for example, in fast and fair, when you are reading a value and another thread is writing a value, you may see duplicate values, but the reader will just ignore this and keep going, right? So this is the sort of mechanism that we are talking about, where the reader has some semantics encoded into it and can tolerate inconsistencies, right? Similarly, writers can fix inconsistencies that they encounter. So while a thread is writing, it creates duplicate values and it's going to change one of those values to the new value, and then it crashes, right? Another thread that later comes along may look at this state where it has duplicate values, and then you can say, like some thread was trying to write and it failed, so I'm going to remove this duplicate value, right? So it can fix the inconsistency. So in the theory community, they call this the helping mechanism, and there's been lots of work about this. But sort of like our chief insight is that this is exactly what you need for crash consistency. You want reads to tolerate inconsistent physical data, and you want writes to be able to fix inconsistent data. So if a data structure already has all of these things internal to it, then it doesn't need anything special for crash recovery. It has inherent crash recovery, right? So that's sort of like the chief insight, and that's what covers recipe. So recipe is still takes some nuance to apply. You can't take any DRAM data structure willy-nilly and then convert it to persistent memory. It only works for certain conditions, right? So we identify what conditions have to hold before you can convert a DRAM data structure to a persistent memory data structure using recipe, right? And here I'm going to give you one example, right? So this is and the paper has all the details, but we call this condition 2, where readers and writers don't hold locks and writers have a helping mechanism so they can fix inconsistencies. So in this slide, what we're seeing is when a writer is writing, it does a sequence of ordered atomic steps. So other readers and writers also know about these ordered atomic steps, and then there's a commit step. So when the writer thread crashes after steps 1 and 2, a reader thread that comes along is able to tolerate this. So it's able to see that, like step 3 and the commit step is not performed, so it's some intermediate junk that's in, let me ignore this. So the reader thread can do that. A writer thread that later comes along can see this and say, the original writer thread must have crashed, and it has some mechanisms to figure out if it's crashed or it's trying to do it concurrently. And then it's going to say, I'm going to finish this. So going to complete step 3 and then the commit step. Now this may either be roll forward or roll back depending upon the situation. But in all cases, the writer is able to finish the job. It's able to return the data structure to a consistent state. Now, now that this data structure can already do this, it's actually inherently crash recoverable, right? If it crashes, for example, then another writer that comes along is able to do the recovery. So we don't have to add in any crash recovery logic. It's already inbuilt into the system. So the only thing that we have to do is remember that this is all done in the context of DRAM. So they think everything is volatile. So they never flush anything to persistent memory. They don't have fences, right? So for crash consistency, you do need flushes and fences. And it turns out that you can actually add them in a fairly straightforward way. Every store has to be followed by a fence and a flush, stuff like that, in order to transform the DRAM data structure to a persistent memory data structure. So that's basically how, with less than 200 lines of code, we were able to convert 5 different data structures from the DRAM form to their persistent memory form. So it's sort of like a very powerful technique. And again, this is again open source. I highly encourage you to check it out. We have put in a lot of effort to make it usable for other people. And if you want to use it in your, company or in your research, we are very happy to help out. Okay? All right. So I want to return to sort of like the bigger theme here. We want to reuse existing code, right? So in both SplitFS and recipe, that's really what you're trying to do, right? So in the case of SplitFS, all the metadata operations are handled by an existing file system, which has seen decades of development. In the case of recipe, we don't add any crash recovery logic. All we do is take advantage of things that are inherently in there. Again, decades of research development into DRAM data structures, right? Now, we want to do this without reinventing the wheel, because even though persistent memory is new, it's very similar to DRAM, right? And there's already been a whole ton of work in DRAM as to how to make data structures and storage systems efficient for that medium, right? Since persistent memory is very similar, we should be able to take advantage of a lot of the things that have already been done in the DRAM world for the persistent memory world. Now, doing this carefully requires innovation, thoughtful innovation, right? I mean, you can't like for example, recipe, you can't take any data structure and convert it to a persistent data structure. You have to think about whether it's correct. You have to think about what conditions this will be correct and what conditions will do this and so on. It requires a lot of thought. But the end result is that it's very easy to maintain. It took a very little effort. And we believe this is a very viable approach to converting DRAM data structures to persistent data structures. So I sort of highly want to encourage more work of this form. So now I talked about new storage technologies, persistent memory, and how we build storage systems for that. Now I'm going to talk about new applications such as like machine learning and how we build storage systems for that. All right, let's keep going. So in recent years, there's been a number of very interesting new applications that have come out for both persistent memory and other storage media. So one of them is machine learning, right? And in here, we wanted to answer two sort of big questions. So one is, does storage matter at all for training machine learning models, right? number of researchers I used to talk to believe that, like, it doesn't matter at all. All you want to do is you want to get the data into GPU, you can use prefetching to solve this, right? And as we show in our work, that's not quite true. And we want to figure out how can we best use the DRAM cache and the GPU memory when training ML models. There's also blockchains, and again, the same question, right? Given that blockchains are so mining intensive and GPU intensive, the storage really matters, right? It also does. It matters quite a bit. And we then show you how to design a storage system to best support public blockchains. And finally, we briefly sort of look at, like, how does the GDPR regulation, how does it affect storage designers, and like, how do we build GDPR compliant storage? So first, we're going to talk about storage for ML. This is ongoing work. We have a preprint up on archive, so highly encourage you to check it out. This is work done by my student Jayashree Mohan in collaboration with Microsoft Research, specifically Amar Panishai at Microsoft. All right, so let's take a look at the training pipeline for a machine learning model. So let's say you have an SSD on which you're going to store your training data. And then you have a number of CPUs on hand. And what you're going to do is you're going to read the data from your SSD into your cache. You're going to decompress, because you usually compress before you write it out to storage. And then you apply random transformations, right? So for example, if you're doing image classification, you take the training data and then you crop it or you rotate it and so on, right? So you apply all these random transformations and then you feed it into your GPUs, right? Now, in this whole pipeline, the GPUs are the most expensive piece of equipment, and you want to ensure that the GPUs are, fully utilized, that they're operating at 100% efficiency all the time. Unfortunately, it turns out that storage is quite a bit of bottleneck in this case. So for example, now we're going to look at the maximum bandwidth from one stage to another in this pipeline, right? So for example, if you have an SSD, you can read the data off it at like 500 megabytes per second, right? It seems reasonably fast. Then if you have a cache, then the effective throughput you get out of your cache is going to be higher. So let's say that's going to be about 800 megabytes per second. You're going to take all your virtual CPUs and you're going to use them to decompress your data. And you can do this at like 1,300 megabits per second. Then you're going to apply random transformations. Then you're going to feed it into your GPUs. And on GPUs, if you have 8 V100 GPUs, you need 2,300 megabytes per second in order to be efficiently processing all the time. If you supply data to it at a lower rate, the GPUs are going to stall. They're going to just be waiting for data to be fed, right? And this whole thing is with prefetching, right? So every component in here is going to be doing prefetching. Even then, the amount of even with full 100% prefetching that you're doing, your throughput is going to be constrained by the bandwidth from one component to another, right? So in this particular case, the GPUs are going to stall, and the bottleneck is you cannot apply random transformations fast enough to feed the GPUs. So 24 vCPUs are not enough for this particular model at this particular GPU configuration for 8 GPUs. We call these preparation stalls or prep stalls. In general, we call anything that stops a GPU from, we call this a scenario where the GPU is waiting for data to be fed in. We call it a data stall. And prep stalls are one instance or one type of a data stall. Now imagine that instead of an SSD, you had a hard drive, right? So now the hard drive, since you're going to be doing random reads, can only give you 15 MB per second. With your input data cache, you get about 23 MB per second. Now that is the bottleneck for this whole pipeline, right? If your decompression threads are only going to be getting data at 23 MB per second, then it doesn't quite matter what the rest of them can do, right? The rest of the system can do. That's the bottleneck. And we call them fetch stalls, right? So your GPU stall because you cannot fetch data fast enough into your main memory, right? Again, this is all with complete prefetching. Even with prefetching, your GPUs are not able to keep up with the rate at which the system is not able to keep up with the rate at which GPUs ingest data. So one sort of like obvious question here is, what if we just did all of this beforehand? We applied random transformations and just keep it ready and then we supply it to your GPU. The answer is that you don't have enough memory. So these steps actually increase the data size quite a bit. For example, before you decompress or like after you decompress, the data set grows by 5 to 7x. We're going to be applying all these random transformations. These random transformations have to be different for each epoch to help the machine learning model learn. So you cannot pre-process all of these things and keep it in memory, at least for certain models, right? So you have to do them as you go along. And it turns out that on current machine learning optimized cloud servers, the system is not set up so that like everything is flowing nicely to the GPUs. There are going to be data stalls. And in our paper, we sort of like look at many different machine learning models across a bunch of different hardware configurations, and we show you how data stalls exist and what you can do about them. So we also built some other tools such as the DS analyzer, and what it does is it can answer what if questions. So what if storage becomes faster? What if we had more bandwidth of the storage? What if the number of CPUs or GPUs is increased? We sort of like the DS analyzer will tell you what happens to the data stalls in this case and what happens to overall GPU training if all these scenarios come about. So we feel that this is going to be a very useful tool for developers, because now they can say, all right, what happens if we throw more storage at this problem? Does this help? And in some cases it does, in some cases it doesn't, and DS analyzer can tell you, right? We also built a new data loading library called Cordia that reduces data stalls. And by reducing data stalls, we see immense gains in the performance of machine learning training, right? So for example, we can speed up hyperparameter search by 5x. We can speed up single server training by 2x and multi-server training by 15x. So there's a lot of like nice insights in the paper, and I recommend you check it out. I'm going to now briefly talk about storage for blockchains that we have been working on. So again, if you look at public blockchains, right, what they do is they release a block every n seconds. Now, the reason they release a block every n seconds is they want to wait for the latest block that has been mined to be propagated and verified by a majority of the nodes. So for example, let's say you have a very, very tiny network, sort of like inside your house. And once you mine a block, it takes only 1 second for all of the nodes to obtain and verify the new block. That means that you can safely release a block every 1 second without giving up any safety properties, right? So the time at which a block is released really depends upon the time taken to propagate and verify a block, right? The time taken to verify transactions, which is the content of these blocks, thus directly affects n, like how frequently can you release a block, right? So we show in our paper that the verification time actually really depends upon how the data is stored and processed, right? Because when you get a block, you have to look up Merkle trees, for example, to sort of like verify that the data in the block is correct. And this is all IO operations. It's an IO bottleneck process, right? So we've designed a new storage system and a transaction processing system to alleviate this bottleneck and to sort of increase throughput. And we show that this increases transaction processing throughput by 20x compared to Ethereum, right? So the archive paper has more details, and I highly recommend you check it out. So now I'm going to talk about our storage for the GDPR regulations. And this was done by my postdoc Supreet, who's now starting as a professor at the University of Iowa. So we analyze GDPR from a systems perspective, right? And the high level thing is that we notice that there's a lot of metadata associated with each data item. This slows down insertions and requires additional indexes and so on. And GDPR also has other requirements like encryption, monitoring, access control, and so on, right? So in general, we call this the metadata explosion because now the amount of metadata the system requires you to keep for each data item is now much higher, right? And we contribute a new benchmark that allows you to test your GDPR compliant storage and to see whether it will perform well on GDPR rules. So this was published in VLDB 2020. Due to lack of time, I can't talk a little bit more about it, but I highly encourage you to check out the paper. All right, finally, I'm going to talk about the new metrics. So write amplification is something that is sort of like something that like companies care about quite a bit, right? So basically, write amplification is the ratio between amount of user data versus amount of I/O written to the storage device. So for example, let's say the client is sending in 10 gigs, and on the server, you see that to storage, you're writing 500 gigs. So write amplification in this case is 50 times, right? Now, Intel SSDs can last, for example, 5 years, assuming a write of like 5 terabytes a day. With write amplification, instead of writing 5 terabytes a day, you can only write 75 gigs, which is quite a bit lower, right? So what this means is companies like Facebook and Google, for example, replace their storage units every, like once every 3 years, for example. And if the storage unit burns out and or wears out, and they are forced to replace them earlier, they have to pay significantly for that. So because of this, they are very careful about write amplification. And we built PebblesDB, which is a write optimized key value store back in 2017. Key value stores like RocksDB have a high write amplification, right? At 10,000 feet level, the reason is because they rewrite data on storage to keep it sorted, so that when you want to do a read, you can very quickly get to the data. The big idea against PebblesDB is that you can keep your data partially sorted, not fully sorted, which has a big cost, but partially sorted, and it strikes a good balance between read performance and write performance, right? So for example, compared to RocksDB, PebblesDB gets between 3 to 6 times higher write throughput while writing like half the amount of I/O to storage, right? Again, PebblesDB is open source, and we've done a lot of work to make it usable to other people. Please check it out and send us an email if you have any questions. All right, so now we talked about new applications and metrics. I'm going to very briefly talk about future challenges, and then I'm going to conclude. All right, so what are the sort of like future challenges in this space when we're building storage systems for all these new applications, hardware, and metrics, right? So for example, persistent memory is accessed via the page tables, right? So it's similar to DRAM. And it requires strong huge page support, because if you have 6 terabytes of persistent memory on a machine, in order to address it and access it, you need to use huge pages. But huge pages today are very fragile. In order to get a huge page, the huge page has to be correctly aligned both in physical space, like on the physical persistent memory device, and in the virtual space. So this means that once you have a little bit of fragmentation, you're not going to get any huge pages, which is really terrible for performance. How do we solve this? And this, I think, needs to be solved with both an architectural solution as well as system solution. And I know like lots of people are working on this, but this is very important thing to solve. How do we build GDPR compliant systems? How do we make it so that mom and pop shops can achieve GDPR compliance? Because like for Google and Facebook, they will figure out how to be compliant, but like really the mom and pop shop who are now forced to be GDPR compliant, how do we make it easy for them? It's sort of like another question that we're tackling. How do we build verified storage systems that support rapid and sustained development, right? So a lot of verified systems that we have today require a lot of effort to prove, right? You need to write, for example, proofs that are about 20 times the number of source code lines. So that is really not a good option if you have rapid development, right? We do have more automatic approaches, but those are again synthesis approaches, for example, done by Shivang and Nator at Washington. Those are more promise. But the goal should be you have a system and then you want to keep changing it very rapidly. You want to still be able to prove something about it. So that's something that I'm excited to sort of work on. Long term, we also have other challenges like how do we build storage systems for mediums like DNA and silica, both of which that Microsoft is working on. And how do we build storage systems for disaggregated setups, right? So what should be the role of hardware? What should be the software interface? How should we handle reliability? So this is again something that I'm very interested in and my group is working on. And finally, how do we democratize machine learning, right? So today, a lot of machine learning is done on like very beefy machines, like like big GPUs and many GPUs, for example. So how do we make it so that like you can still do machine learning, but on significantly slimmer machines where the memory consumption, for example, is like much lower, or the storage bandwidth required is much lower. So again, my students are working on this. So to conclude, it is a very exciting time to be a storage researcher, right? 20, 30 years ago, it was not as exciting, right? We only had hard drives. New storage devices are there, new applications are there, all bringing new challenges. And my sort of like appeal to the research community is that they should reuse existing systems and data structures as much as possible. And doing so thoughtfully requires a lot of innovation. And future challenges will require interdisciplinary collaboration, right? So for example, when you're developing PebblesDB, we collaborated with like Itai Abraham at the VMware Research. A very fun collaboration. In general, like Rob Johnson and others at VMware Research, at Rutgers, for example, we're all doing great work in this space between theory and systems. And I'm on the PC of a conference where, again, we're looking at work at this intersection, right? So I would highly encourage system folks to collaborate with theory folks. There are large gains to be had on both sides if the collaboration sort of works out. With that, I'd be happy to take any questions, and thank you very much for having me for the keynote.